I'm really pleased to introduce Mikayla. So Mikayla is a second-year PhD student at UTIG. She received her bachelor's degree in geology with a minor in mathematics from Middlebury College, and she is broadly interested in glaciers and ice sheets, with a particular focus on numerical models to understand feedbacks between glaciers and the rocks underneath them. Her current work focuses on the feedbacks between glaciers and the sediments they produce, and she will be applying the expertise gained from this work during an expedition to Greenland next summer as part of the Terminus project. So go ahead.
Test. Okay, cool. You can hear me? Great. Thank you, Alice, for that lovely introduction. And thank you all for showing up on this awesome Friday. It'll be exactly 1 week where I do this on another Friday morning. So with that, I would like to thank my co-advisors and collaborators for the help within this project and also our funding sources. So a quick introduction, and starting with this plot here on the right from NASA Earth Observatory. This is the western coast of Greenland, and you can visibly see that there's the large Greenland ice sheet. There's the Labrador Sea, some cloud coverage from the satellite image, and something that sticks out to me and something that motivates this work is the large amount of sediment plumes coming out from the coast. And you can see in some areas there are larger area coverage of sediment plumes, and in others there's not. And so we're curious and motivated about why do some glaciers have a lot more sediment compared to others, and what impact does this sediment have on large outglaciers? Could it be a combination of the climate gradient, bed slope, topography that it interacts with, the amount of sediment present? These are questions that we're motivated to understand. And so I attempt to understand some of these questions through a finite element numerical model adapted from Brinkerhoff and others in 2017. This numerical ice model was originally made for Taku Glacier in Alaska to understand the sediment interactions there. And so what we did is upgraded it to the idealized Greenland fjord setting. And so some of the components of this model briefly are having an ocean interaction, so the presence of ocean water. We represent sedimentation through glacial fluvial and diffusion processes, which means that glacial fluvial is water from the surface of the glacier that's routed to the bed topography, and it transports sediment under the glacier and deposits in front of it. And then diffusion occurs in the marine environment where you can push these moraines, build them up, and diffusion is like pushing them down and moving them away. So that's the sedimentation component of this ice sediment model. But what we're largely interested in are the changes in bed topography and surface mass balance to just understand what are these idealized glaciers around Greenland and what happens in this parameter space as we try to make a relationship between ice and sediment dynamics for most outlet glaciers around the world. And so what does this parameter space look like when we change both SMB flux gradients and slope? On the y-axis, we have the SMB flux gradient, or like a climate kind of proxy. So a low value is something arid and dry, like what we think of Antarctica. And then larger numbers are what we think about when we see like temperate glacier climates like those in Alaska. And then for bed slope, different bed slope topographies on the x-axis, low values represent shallow sloping topography, while large numbers represent steep sloping topographies. So a large parameter space, and next I'm going to walk through one of these ensemble members and the model setups that we do to isolate the effects of bed erosion, bed change, and sediment. So through 4 control or initial model startups that I'll walk through these next 4 ones. The top panel is the ice profile over time, and then the bottom panel, we have ice volume over the entire simulation. For all of these simulations, they run over 50,000 years, so we're thinking what change is happening on millennial timescales, and then what's happening to the profile or the ice profile, the bed topography, what kind of sediment's being built up. And so our first and initial control is having a run that has sediment off and bed change off. When we talk about bed change off, we're interested in how we treat erosion and the amount of sediment being produced. And so here in this first case, we don't want any sediment and any bed change. This next run, you see that the orange curve has some mounds forming or moraines. And you can see in the black line, which is the bed topography, it's not being eroded or having like the little bumpiness that you might see in like a seismic profile. And so what this means is that erosion is happening. So sediment is being produced, but what's happening is that the bed topography is immediately replaced. And so it stays constant. So we have sediment, but no bed change. For this next run, it's similar to the first one, but the difference is that we have bed change occurring. And so I wanted to blow up and speed this up a little bit. And so you see that over time, so this is like around like a 30,000 year time scale, you can see that the bed topography is actually going down a little bit in elevation. And so this is like the bed change that's occurring, but the sediment isn't necessarily building up. And then our final setup, which is both sediment on and bed change on, you can see that in the black line, the bed topography has been eroded a little bit over this time scale. And then sediment moraines are being produced and we get tidewater glacial cycles. And so here are 4 model setups to compare and isolate what are the effects of having bed change or bed erosion within these model setups and also sediment. And so my big takeaway is that we have either increases or decreases in modeled ice volume. And so the parameter that we use to compare the differences in sediment simulations or bed change simulations is through this difference or deviation. So on the right side, we have the upper plot, which is the ice volume plots that we've seen in the previous slides for these model setups over time. And the bottom is just a subtraction of the two. However, this color represents the percentage of that deviation over the entire time. And so we can either have a positive or red a modeled ice difference between the two, or blue, which is like negative modeled ice line between the two. But in this case, when we compare the sediment on, bed change off, and sediment off, bed change off, we can see a total positive deviation here on the right, and these colors will stay the same throughout this slide, comparing these different simulations. Here you can see on the bottom deviation plot with the green line, it's kind of negative trending, and so it's not as positive as the previous one where it's like a 15% total modeled ice volume increase compared to these two, but something a little bit less overall. Here, these lines look pretty similar, but that plot on the right looks pretty interesting in terms of having either like a total positive or total negative difference between the two, but this is like a small total positive ice volume deviation. And then the same for the next plot too. These with the ice volumes just looking a little bit different, but when you take this deviation, it's actually not too major of either a total positive or negative deviation. And so comparing these different members and doing this deviation calculation and bringing it back to this plot, we're curious if this holds true for the entire parameter space, if we're going to see all red or all blue across these different subtractions. And so when we look at only sediment, so isolating the effect of sediment compared to a no sediment case, we see that there's more modeled ice volume across this entire parameter space. However, when we're interested in isolating the bed change effect, we see that we get negative deviations. And so how we can interpret this plot and what this means and the animations that I've seen within my analysis is that for negative deviations, the erosion that's occurring actually prevents the glacier to advance. And then for the positive deviations, we see that the presence of sediment allows this glacier to advance. So 2 opposite sides, and then what's in the middle is that these 2 interactions actually keep up with each other. So in conclusion, we see that through bed slope and surface mass balance gradients, we see this glacier sediment interaction where we isolate sediment, we see positive ice volume deviations, where with erosion we see negative. And so through this ensemble, we can disentangle these complex interactions between sediment, erosion, and bed changes. And so, yeah, I'd like to thank my collaborators, funding sources, and also say that we're headed to the field next summer to Western Greenland to collect observations and rates of sedimentation. So if you're interested in getting involved in any of this work, please reach out to me or my advisor, Jenny Catania, for any field or computational.
Does anybody have any questions for Mikayla?
Benjamin, have any questions online by any chance?
I have a question. So this might be a dumb question. When you're on your plots, your glacier has a little pokey bit out the front. What's the pokey bit?
Yeah, no, that's a great question. So you can kind of think of it as like an ice shelf or an ice tongue that you might like see in Antarctica. But for some of these like longer simulations, when they play where it's like, let's see, I don't think this one will do it. But it'll like extend like really far out and you might get like a really thin like ice tongue. You can think of it as just like a very thin like sea ice layer too that doesn't really have any like buttressing effects like on the ice as well. But for like the smaller ones that you might see, there's just like a mini ice shelf.
Thank you very much.
Well, something I haven't asked before, but it just occurred to me. If we have a difference in ice volume, could we actually calculate the difference in water flux leaving the glacier in the different cases?
A good question.
Like, rolling it back to a meltwater implication, if you will.
Right. Well, let me think. We do have like a meltwater like representation parameterization in here. And I think something that we might be able to like, what's the word? derive from that is like looking at the sedimentation or erosion volume happening like at the terminus. So in theory, yeah. Right. Yeah. I'll try it.
So coming from someone who doesn't know anything about the Earth or Earth glaciers, is the sediment type change between these glaciers? Are they more or less like the same types of sediment in terms of like composition and grain sizes?
Yeah, that's a good question. So with this model, we treat it all the same, but in reality, obviously they're different upstream, downstream. Do I know the different types of composition? No. So yeah, you might have to ask other people in the room who look at marine sediments for that.
Okay, thanks.
Okay, quick transition to Ethan then.
Thanks, y'all. Oh my God, I'm messing up. On.
Oh, nice. Check, check, check. Yeah, that's good.
Oh, I think you're good. Have you used this before? You want to use it?
Sure. Yeah.
The pointer is the top one.
Okay. The next slide is also okay.
So, oh no, my phone has turned off. There we go. I also have the pleasure of introducing Ethan. Ethan is a fifth-year PhD student working with Torsten Becker and Danny Stockley. He received his bachelor's degree from the University of Florida. He's broadly interested in tectonic geomorphology, focusing on a word that I typed this morning, but I now can't read, exhumation in, deformation.
Deformation, yeah.
There we go.
Yeah.
And exhumation in transpressional systems and the linkage between tectonics and surface processes. So take it away.
Thank you, Alice. Yeah, when I practiced this, it was 8 minutes and 40 seconds. So I'm gonna try to get through it, but I'm gonna record myself. So yeah, so I'm gonna talk about the morphotectonics of transpressional systems and what we can learn through erosion tectonic sandbox modeling. So on the left here, we have some examples of transpressional systems in nature. On the top, the Merida Andes in Venezuela, and the bottom, the central transverse ranges. They're both characterized by, they're both thrust-bounded wedges, characterized by a partition master fault, and they exhibit highly irregular drainage networks that are expected in these transpressional systems. On top of that, I've superimposed some thermochronometric dates, and we can think about how to contextualize these dates within some sort of process framework or model for how transpressional wedges evolve. On the right, I have some questions related to the evolution of transpressional systems. For example, how do streams respond to the structural evolution of the wedge? How does the topography correspondingly shaped by these streams and other erosional processes? How does exhumation change across the wedge? And how does strain partitioning evolve throughout the evolution of the system? So what we can do is we can use erosion tectonic sandbox models to study the feedbacks between these processes. On the left, I have a drawing of the model that we actually use. So it's a 2 by 1 meter plexiglass box. Inside that box, we put a plexiglass board that was cut to a desired convergence angle. Beneath that board, we pulled a mylar sheet. And the discontinuity in the velocity field between the moving mylar sheet and the fixed plexiglass board nucleated deformation over that velocity discontinuity. On top of the board sheet setup, we loaded a material package comprised of silica powder, glass microspheres, and PVC powder. And then on top of the deformational wedge that formed, we used a misting system to nucleate surface processes. We recorded the evolution of the model with 2 cameras and a laser scanner to generate digital elevation models. And you can see what the actual setup looked like in the small inset. So here's the results of our laser scans. So going down the rows, we're looking at separate models. So these are going to be our dry reference model, a low erosion model, and a high erosion model. And I'm calling these low and high erosion models because they represent differences in the intensity of tectonic and surface processes. So this is captured by the ratio between the convergence and the rainfall rate. And then looking across the columns, we're going through different shortening stages that are representative of key moments during the evolution of these models. So we have the 30% shortening, 70% shortening, and then the final 100% shortening stage. In the first stage, prior to erosion, we see generally the same topographic characteristics. We see these rhomboidal pop-ups that are coalescing to form our divergent wedge. However, when we move to later stages, we start to see significant differences in the topography between the erosional systems. And that's made even more clear by these high contrast images. So on the left, we have the high erosion system where we can see this clear axial valley that's being formed across the axis of the model. Whereas in the low erosion system, we don't have this clear axial valley. We see that there might be this incipient valley starting to form, but we haven't got to that stage yet. We also see some beautiful alluvial fans forming off the left side of these wedges, and that there's just generally more incision in the high erosion model compared to the low erosion model, as would be expected. The structural evolution also differs between erosional conditions. We see in the initial stage this generally reproducible system of N-echelon R shears with the initial formation of these anti-Riddell shears and our more low-angle Y and P shears as highlighted in magenta. And then as we move to later stages, we see that in the high erosion model, there's more low-angle faults that are forming earlier. And that's captured in these polar histograms, where in the high erosion model, in the salmon color representing the final stage, we see more faults in these low-angle bins between 0 and 15 degrees. Looking at shear strain or maximum horizontal shear strain derived from particle image velocimetry, which is going to generally represent strike slip deformation during the evolution of the system, we see that there's some key differences between the models in this space as well. So again, initially we have strike slip localized to the wedge bounding thrust. This is expected in an unpartitioned transpressional system. But as we move through our shortening stages, we see that erosion seems to accelerate the shear strain partitioning. And that's made clear in this middle bottom panel here, where you see the localization of the maximum horizontal shear strain to structures that are subparallel to this velocity discontinuity. Whereas in the low erosion and dry model, the system is still relatively unorganized. And that's just highlighted here by these glowing polygons showing the partition through-going master fault. And we attribute this to a reduction of overburden, which would unclamp the master fault, a reduction of the vertical stress over the wedge bounding thrust, and then accelerated slip on those wedge bounding thrusts would lead to unclamping within the wedge as well. We find that drainage networks are also distinct among erosion models. We have the low erosion models on the top, and then the high erosion model in the bottom, again with the shortening stages going across the columns. In the high erosion model, we see more vigorous drainage reorganization. That's represented by these captures or diversions shown in the blue dots. We see that there's an active response to the faults that's occurring earlier. We know that streams follow weaknesses that are derived from fault systems. And we see that the surface processes are starting to follow these earlier in the high erosion model, whereas that response is slightly delayed in the low erosion system. And these things lead to characteristic drainages between the low erosion and high erosion models, where we have more asymmetric or forked drainages in the low erosion model, but these rectangular drainage geometries in the high erosion model. And these are going to have implications for many features within the wedge. For example, where exhumation will be localized across the wedge, your ridge valley structure, some of those questions that we posed in the beginning of the talk. For one of those, when we think about where exhumation is localized across our wedge, we can do a simple exercise where we take a swath profile, in this case across the high erosion system from A to B, which is shown in this salmon color again. And that's going to represent erosion by transverse drainages. If we draw a surface over that swath profile, shown the dotted line, and consider this rock uplift, the area between that surface and the swath can be considered erosion by longitudinal drainages, those that are perpendicular to the swath profile. And we see that the estimation for exhumation is the narrowest above that through-going axial valley, where you have this continuous erosion signal from the longitudinal drainages because they are it's spatially continuous across the width of the swath. So we can sum all of this up into a synthesis model for the characteristic evolution of a transpressional wedge, where we start with an echelon Riddell faults, which ultimately coalesce and pop up these rhomboidal landforms. At this stage, you have shear strain partition to the wedge bounding thrusts. And then we see differences between the low erosion and high erosion models, where in the high erosion model, you have accelerated partitioning of strike slip to this through-going master fault, which is co-located with a through-going axial valley. You see differences in the drainage networks where you have more rectangular drainages in the high erosion model. And these may ultimately lead to some final stage where, because you have high partitioning to that through-going fault, you have kinematic offset. And now we can return to our natural systems and start to think about what we see in the patterns of the thermochronometric dates across the maps. We see the highly partitioned through-going fault in both of our systems. And we see that the youngest thermochronometric dates, though not super spatially dense data, those youngest dates are above that master fault and axial valley. And so with that, I'll leave you with some key points and I'll take any questions.
Any questions for Ethan?
So how did you quantify the amount of erosion relative to the rainfall that you put into the system?
Yeah, so we didn't quantify the amount of erosion, but we considered the intensity of erosional processes to be captured by the amount of mist that we put onto the system. And so we only varied the convergence rate, but left the mist constant because it's just more difficult to get a uniform cloud over your wedge. So for the high erosion model, it would be one with a slower convergence, but the material strain rate independent, so the convergence didn't matter. It's so that difference in the ratio should be what's controlling the system. Yeah.
Follow up. Yeah, I'll do a quick follow-up. Did you attempt between the different cases to actually quantify the sort of maximum principle, or really the minimum principle, I guess would be the important one that changes because of your overburden?
We made attempts. It's kind of a challenging problem. The stress field within the wedge is very complicated, and we don't have good. All we have like as far as hard numbers are the convergence rate we set, and then we have the PIV, but the PIV can be the particle image velocimetry can be highly affected by the rainfall pattern. So what we see as far as the partitioning, it's kind of this coarse signal that we can't really derive anything quantitatively out of. You can start to think about how the stress field would change. For example, I mentioned that the vertical stress is going to change over the wedge bounding thrust, and that's going to lead to kind of this unclamping effect. And so we more think about it like from a point of intuition, like, okay, you're in an unpartitioned thrust fault, your sigma 3 is going to be oblique to the vertical. But as you remove material, it's going to trend towards the vertical stress is ultimately going to be the sigma 3. But yeah, we were unable to actually get to show that. We actually, I mean, just for this audience, we actually just ended up saying the unclamping effect should just scale with rho GH. So if you reduce H, then the mean stress in the wedge, or the background stress, is going to go down. And so, yeah.
I have a quick question. So you showed two examples where you were comparing observations to your models. Is there anywhere else that you think it would be good to get observations from?
Yeah. So 70% of plate boundaries have an oblique component. These systems that we tested are representative of high obliquity. So something that's near strike slip with maybe like plus 30 degrees of convergence. So really anywhere where you have that, the results of our models could be applied. Some examples include like the Alpine Fault in New Zealand, I guess the Denali Range in Alaska, and the Western and Central Cordillera has a more perpendicular convergence vector, but still we can still learn about this system from these models. So yeah, there's several other things, but in nature, you're going to have so many confounding variables that many of these more detailed signals that we see can be washed out by those things. So it's somewhat difficult to make those comparisons, but this gives you a good baseline idea of what can be expected without climatic gradients or lithological variation.
Very much.
All right. Almost stripped. That's a great introduction. I'm going to be confused by her talk, I was just told.
Gonna be
But it'll be fine.
I'll
All right,
take
it's my pleasure to introduce Carson Miller. She's I guess 4th year now, right? Is it 4th year? PhD? Yeah, right. I lose track. Carson and I actually share an alma mater. We both went to University of North Carolina at Chapel Hill. And then she has done a master's degree with Tony Rodriguez, which is an interesting side note story because she is now actually in her first paper testing her former master's advisor's ideas about the banks off Texas at the University of Texas, which is kind of cool. Anyway, so she works with John Goff and I, also Chris Lowry, on Texas continental shelf, basically sedimentary evolution, and has particularly been focusing on questions about the evolution of barrier islands and paleo-barrier islands, whether they get preserved. And this is her AGU talk related to her first paper that we now have in hand. So, Carson.
Awesome. Thanks, Sean. Hopefully this is going to be under 8 minutes. It was 7:57 the other day, and this morning it was 9:40, so we'll see what happens. Okay, so I'm going to be talking about Sabine and Heald banks, which are on the East Texas shelf. And before I do that, I just want to kind of give context to this study. So we are funded by BOEM to look for offshore sand resources to be used for beach renourishment projects. And so I want to talk a little bit about where does sand come from in a barrier island system. So back when sea level was much lower, our rivers actually incised into the continental shelf, creating accommodation for estuarine sediments to then fill, which is what I'm showing in this orange line. And so the top panel is showing the environments, the bottom panel is showing where it would be deposited. And so our first most superficial sediments are going to be our highest energy environment. So that's going to be things like overwash inlets, ebb and flood tide deltas, and then barrier islands. Because they're so high energy, they're most likely going to have a lot of sand in them. Barrier islands are in yellow because they typically don't get preserved in the geologic record. Moving back into your central bay, it's a much more quiescent environment. And so you get lots of muds, not a very good sand resource. Moving into the Bayhead Delta, this again is yellow because it may or may not be a very good sand resource, depending on how much mud you want in it. So if it's closer to the Central Bay, you're going to have a higher mud proportion, but if you're closer to the river, you'll have a higher sand content. And then finally, fluvial deposits, again, high energy, lots of sand, but they're also going to be very deep. So preservation of these environments at the coast is really a balance between sediment supply and accommodation. And so in order to actually drown barrier islands, you want to maximize your accommodation, but minimize your sediment supply. And then to preserve these environments, you want to maximize both accommodation and sediment supply. So this is our study area. There are 2 sandbanks, Heald and Sabine. So Sabine is in the northeast, Heald is in the southwest. They're the blue blobs underneath all these seismic lines. We have about 1,700 nautical miles of seismic data across the banks. There are 31 cores from Rodriguez et al. 2004, that was my old advisor. And he has 16 that have published stratigraphic information, and of those 10 have radiocarbon dates. I also want to point out that there will be more cores collected in this area later. So the main objectives of the study are to identify sand resources. So paleo-barrier islands are really good candidates because they have similar grain size and color as modern day beaches. But then we also want to understand the processes controlling preservation. And then this is going to help us start to predict the location of sand resources in other regions. So this is our internal stratigraphy of Heald and Sabine Bank. So Heald is on the left, Sabine is on the right. So the top panel is uninterpreted, second panel is horizons, third panel is units. So one thing that you might notice about Heald versus Sabine is our transgressive ravinement. So this is left over as the barrier moves by. Underneath Heald, it's pretty much at the base of that bank, whereas with Sabine, it kind of comes up and over the bank. So anything that's deposited below that is going to be potential barrier island or estuarine, and then anything deposited above that is going to be marine. So Heald is most likely a marine sand body, while Sabine is more likely to be a paleo-barrier island. There's another unit that's underneath Sabine that we don't see underneath Heald that also indicates that it could be a potential barrier. So this is our unit 2. It has landward dipping, very high amplitude reflections. That's our U2. I also want to point out just very quickly that our U4 at the very base is going to be our estuarine unit. So it's kind of got medium amplitude, kind of draping reflections. And so that's indicative of a estuary. So I was able to take Tony's scores and then put them onto my seismic lines to try to get an idea of the stratigraphy that's within Sabine Bank. So there's a few things I also want to point out here. So the first is that there's kind of 2 different seismic characters of this unit 2. The first is going to be the lower amplitude portion that's more seaward. It also has higher sloping reflections. And this actually correlates really well with the Rodriguez 2004 shore face unit that is very sandy. There it is. And then we also have this higher amplitude, lower slope section that is more landward. And this correlates really well with his estuarine unit, so interbedded sands and muds. So this is also, again, really indicative of overwash. And so the other thing that he has is radiocarbon dates. And so he says that Sabine drowns around 4.7 thousand years ago. But within this overwash unit, we do have radiocarbon dates that indicate that overwash was actually active between 7.2 to 2.5 thousand years ago. So Sabine would have had to drown after this date. There they are. There's all of them. Okay, so why does Sabine ultimately get preserved? I'm showing you again that sediment supply versus accommodation, so we can start to think about how these different factors influence both of those. So in terms of sea level rise, within that 7.2 to 2.5 thousand years ago, rates are actually decreasing from 1.4 millimeters a year to 0.4 to 0.6 millimeters a year. That starts around 4,000 years ago. So in this case, we're actually decreasing the rate of accommodation creation. And so we're not really maximizing accommodation with sea level rise when we think about a barrier island system. It's pretty large. So not really important for preservation or potentially drowning. Next up is antecedent topography. So I was able to create this hypothetical boundary that's in the red. So this is basically the accommodation space that is related to the Paleo-Sabine incised river valley. So I just drew a line across from one edge of the valley to the other. Anything below that is going to be our accommodation associated with that valley. I told you that U4 is our estuarine unit. And so that is mostly filling our accommodation within the valley, but anything between that black line, which is the top of the estuary, and the red line is going to be our accommodation that our barrier sediments could potentially infill. So when we look at a map of it, you can see maybe, can you see this? Yeah. Okay. That most of our accommodation is underneath Sabine Bank, and we essentially have no accommodation underneath Heald. But even when we look at this, it's only about 5.3 meters of accommodation, which really isn't that much when you're thinking about a huge barrier island. So again, not really maximizing our accommodation in terms of antecedent topography. So we're gonna throw that one out as well. Thinking about the low gradient of the inner shelf. So this is a modeling study by Justin Schaller from 2020, where he looked at different slopes of your shelf. And so in this case, when you have a negative slope or a landward dipping slope, you actually get drowning of the barrier, and that mostly has to do with increasing the amount of back barrier accommodation. And without excess sediment, you are going to drown your barrier. And not just that, but you also produce this thin shelf deposit. And so that's really similar to the geometry of our unit 3. So yes, probably important for drowning and also for preservation of Sabine. And finally, I just want to quickly talk about sediment supply. So during this time period, the Mississippi River Delta is shifting quite a bit. It is a big supplier of sand to the Texas coast. And so back 7.5 to 5,000 years ago, the Mississippi River Delta was all the way to the west, supplying the coast with lots of sediment. As you move through time, so 5.5 to 3.8, you're starting to shift all the way over to the east by about 2,000 years ago, which again is probably when Sabine drowned. So initially, you have all of this sediment coming to the coast, helping build your barrier island, creating a really massive barrier island. And then once it actually shifts away, you no longer have that sediment supply, and you drowned and preserve your barrier. So again, probably really important for both the drowning and preservation of Sabine. And so that's really all I have. And it was 9:20.
Okay, questions? Anyone?
We only have 40 seconds, so.
Huh?
We only have 40 seconds.
Oh, well, that's fine. I have a dumb question.
Yeah.
All of my questions are dumb. So when you're comparing your cores to your seismic interpretation, do some of the cores have an extra layer in them?
Not like different from our seismic?
Yeah.
No,
Okay. I just can't read them. Thank you.
no, it's okay.
I'm not used to looking at them.
Nice job, Carson. How deep are the cores that you have collected in the region?
So we tried and we have like 1 meter cores, but these are from an old paper, and I think the deepest core is maybe 3 meters. Not very deep. It's really hard to core the banks.
With the new cores that you're going to collect, what is your plan for like depth extent of those cores?
I have no idea. We're actually not involved in the collection of the cores. Another institution is going to be doing that, but we're hoping to have access to them.
Awesome, thanks.
Yeah, sand is hard to core.